speaker is Ualbai Umirbaev. I hope I pronounced it correctly. He's going to talk.
It's okay.
Yeah, he's going to talk on representations via differential algebras and equationally Noetherian algebras. Please start.
Thank you very much. So I'd like to thank organizers for the invitation to give a talk at this conference. And I would like to congratulate again on the anniversaries Valeriy Bardakov and Andrei Vesnin. So my talk about representations via differential algebras and equational Noetherian algebras. This is a joint talk with Alexander Mikhailov and Manat Mustafa. So I want to explain what does it mean equations over those algebras. This abstract definition is here. Let M be an arbitrary variety of universal algebras, and let A be an arbitrary algebra of this variety. So denoted by this symbol M of x1, x2, xn, the free algebra of this variety generated by x1, x2, xn. So then we can consider all algebraic homomorphisms from this free algebra to algebra A. It is defined by M tuples A1, A2, AN. So you can send x1 to A1, x2 to A2, xn to AM. And in non-commutative geometry, they like this form of representation of AN. But it's not enough for us. Okay, in this case, even so, every element of this algebra M represents a function from AM to A. And we can consider for any subset, or it shouldn't be B, it should be this algebra, free algebra, define the set of zeros. So it is a set of zeros, all M tuples from AM that satisfies this equation. Polynomial f from this. So this allows to define something like the risky topology, in fact, on AM, but it's not enough. We want to consider in the case of fields, it's okay if A is a field. If A is algebra here, then we have to consider something more. We have to consider something like free algebras over A. So for this reason, I will consider coproduct of algebras. So we take, in fact, consider the coproduct. It's free product of algebras. So it's in this variety M, the same algebra A and the free algebra of this variety. In group case, it is the structure of this free product is well known. In many cases, it is a difficult construction, in fact. By definition, it means there exist homomorphisms alpha 1 from A to B and alpha 2 from this free algebra to B, satisfying some universal property, is usual property of free product here. But these maps, alpha 1, alpha 2, they are not always injections, in fact. So you cannot identify A with its image or free algebra with its image. There are some difficult varieties, in fact. But we assume that A, alpha 1, alpha 2 are embedding. So it is good varieties only we consider. So it is A can be identified by its image in B, and this free algebra can also be identified by its image in this free product. Okay, under these conditions, again, we take M tuple from this algebra, and there is a unique homomorphism from B to A such that phi on A identical, and the xi will be sent to AI for all I. And for any generalized polynomial from B, we said if we can define its image, that just image under this homomorphism. So again, in this case, you can, for any element, generalize polynomial f from B. You can define a function from AM to AN. And for any subset, you can consider zeros of this polynomial. Zeros of this polynomial. So set of zeros, it allows to define the Zariski topology on AM. And algebra A is called equationally Noetherian if AM is Noetherian with respect to the Zariski topology for all natural M, in fact. So there is, with respect to the Zariski topology, it should be Noetherian. In this case, it's called equationally Noetherian. Okay, examples. I started exactly from groups because so many people know about these results. So Ruba proved in 1986 free groups are equationally Noetherian. He used representation of free groups via matrices of order 2. It is just beautiful representation, and it was used here to prove this. Then Bauslak, Mesnikov, and Remesnikov proved for linear groups over Noetherian domains. It includes polycyclic groups and the finitely generated Metabelian groups. So they are equationally Noetherian. Then Gupta and Romanovsky proved finitely generated free solvable groups are equationally Noetherian. Zela proved that torsion-free hyperbolic groups are equationally Noetherian. Where it come from always, so it's here, all of these things. In fact, Harlampovich and Mesnikov and Zela, in their work, when they solved Tarski problems, they used this Zariski topology, in fact, in many cases. Irreducible varieties, coordinate groups, and so on. They use this. So after that, it becomes, in fact, this, I started here from free groups, that they are equationally Noetherian. And Romanovsky suggested me to prove this or suggested this problem for free associative algebras and for free algebras. Notice that these questions for free associative algebras, for free the algebras, they still open. There are no representations like matrix by matrix of order 2 in the case of linear algebras, in fact. So it was proved some general results by Danyarov, Mesnikov, and Remesnikov. So they created some basis over any algebra, algebraic geometry notions. So if A is an equation, let A be an equationally Noetherian algebra, then the following algebras are equationally Noetherian. Every subalgebra of A, interesting. Every direct power of A. Every algebra of the quasi-variety of algebras generated by A. Every free algebra of the variety of algebras generated by A. It's a very interesting general result. And using this, I can give more examples of, in the case of rings and algebras. So classical thing, I was supposed to give this one first. Every field is equationally Noetherian. So it's a Hilbert's basis theorem. It's a corollary of Hilbert's basis theorem. And the same Hilbert's basis theorem implies that every domain is equationally Noetherian since it's embeddable into a field. So it's by using that theorem. Fields are equationally Noetherian. Everything embeddable there is also equationally Noetherian. Every Noetherian ring with identity is also equationally Noetherian by Hilbert's basis theorem. Okay, then the same authors proved that finitely generated Metabelian and nilpotent Lie algebra or nilpotent Lie algebra is equationally Noetherian. Romanovsky and Shestakov proved that finitely generated free Metabelian Lie algebras of character 0 are Noetherian with respect to equations in the universal enveloping algebras. This is in more generalized form of those equations. So in fact, in the case of rings, there were no more results in this direction, in fact. Now, first theorem, we say the following. We consider let R be an arbitrary associative commutative equationally Noetherian ring with identity. We have some examples there. Let A be an arbitrary R algebra that is finitely generated free module over R. In fact, it is, in other words, A is a finite dimensional R algebra. Then A is equationally Noetherian R algebra. So we can use here, in fact, just Hilbert's basis theorem. And using this, it's possible to prove. So corollaries we get here. Every algebra of generic matrices over an equationally Noetherian associated and commutative algebra is equationally Noetherian. They are free algebras of the variety of algebras generated by matrices. Every free algebra of the variety of associative algebras generated defined by the identity is a product of commutatives and commutative is equal to 0 is equationally Noetherian over good region. So why it is? It's just triangular matrices, in fact. It's finite dimensional generated. And the same result, analog of the same result is true for Lie algebras. NCA algebra, Lie algebras over infinite field is equationally Noetherian. So in fact, over regions should be. Okay, it's elementary examples. Now, in this work, we will extend some class of algebras, equationally Noetherian algebras using differential rings. So it's, I give definition of differential rings, in fact. It's differential rings, you have to have some basic set of derivation operators, delta 1, delta 2, delta m. A ring R is a differential ring if it has delta m derivations, m derivations, and those m derivations commute between themselves. They commute each other. So the best example of differential algebra is just polynomial algebra C. C should be m here, of course, in m variables and with derivatives, just partial derivatives. They commute, of course. So it is the differential algebra, in fact. Now, if you have only one derivation in the basic sort of derivations delta, then differential rings are called ordinary differential rings. So you can denote in this case easily derivations by prime. By prime, A prime, it's first derivation, A3 prime, it's third derivation, and so on. But if you have more than two derivations, in this case called partial differential rings. They are more complicated, in fact. Okay, now we consider the set of all derivations. We can make from them free commutative monoid, and theta is an element of this free commutative. It's called theta is called derivative operators. So let R be a differential ring. By RE, we denote a free left module with basis theta. So it's considered differential operators, and they are linear combinations here. Theta is a differential operator, product of derivative operators, and R theta is just element from R, so it's a linear combination. And the product is well defined. In fact, in this case, it looks like, for example, it looks like array extension of rings. This is, in fact, array extension of rings. And the RE is called universal enveloping ring. It corresponds to this notion. Okay, now I want to represent here differential polynomial algebras. So R be a differential ring. X is an independent variable, differential variable. What does it mean? Differential polynomial algebra in one variable. So it is in fact polynomial algebra in infinite number of variables, x, x prime, x2 prime, and so on, all derivatives included. I consider only one derivation case. It's easier. Okay, in this case, now derivation on this ring, it can be extended. If xi prime, if you differentiate it, you get xi plus 1. It's standard. Okay, so you get in fact Rx, in fact differential polynomial algebra in one variable. It's in fact polynomial algebra in infinite number of variables. In general case, if it's not one derivation, so you have to consider a set of x theta, all derivations in fact. Then take the linear combination in one variable. Okay, so we can define in this way differential algebra in one variable over R. It's called the ring of differential polynomials in one variable x over R. Okay, so you can add, as usual case, if you added one variable, you can add another variable and so on. You get differential polynomials in differential variables x1, x2, xn over R. Okay, it has some basis, which consists of some monomials, which is product of xi's, and every element of R can be written uniquely in this form. So it's coefficients and the monomials, differential monomials. And now, so we are in the case of differential algebras. If you consider only just ideals in this case, it is not good because there is operation derivation operator. Okay, just here I formulated Hilbert's basis theorem. If R is a Noetherian ring with unity, then so is Rx. Every finitely generated associated commutative algebra over a field is Noetherian. It's just now in the case of differential algebras, we consider only differentially closed ideals. So if A belongs to this ideal, then its derivative it should belong also to this ideal. So differentially closed differential ideals. Okay. But with respect to differential ideals, here an analog of the Hilbert's basis theorem does not hold. For example, if we in this polynomial algebra in one variable, if you take ideal differential ideal generated by x squared, x prime squared, xn prime squared, and so on, then it is not finitely generated as a differential ideal. So Hilbert's analog of this Hilbert's theorem is not true. But if you consider here not only differentially closed, if you consider plus radically closed ideals, so what does it mean? Ideal is called radically closed if n belongs to I for some natural n, then A belongs to I. An ideal I differential is of a differential is called radical differential ideal if I is radically and differentially closed. So we have to consider in this case radically and differentially closed ideals in the case of differential rings. If you consider this now, a differential ring is called radically Noetherian if it satisfies the ascending chain condition on radical differential ideals. Or equivalently, every radical differential ideal is finitely generated as a radical differential ideal. And here is an analog of the Hilbert's theorem. This theorem is called the Reed-Randenbusch basis theorem. If R is a radically Noetherian differential ring with unity containing field of rational numbers, its necessary condition, then Rx is also radically Noetherian. So this is an analog of the Hilbert's basis theorem for differential algebras. And as a corollary, every finitely generated differential algebra over field of characteristic 0 is radically Noetherian. Characteristic 0 it already you have to use because of Q here in this theorem. Without Q, it's not true. Now, so this theorem already gives some examples of differentially equationally Noetherian differential algebras. Examples of equation, so examples are following. Every differential field of characteristic 0 is equationally Noetherian. So it is differential algebraic geometry is based on this theorem, in fact. It's also, you can say, every differential domain of characteristic is equationally Noetherian because it's embeddable into a differential field. Okay, now let R be an associative commutative ring with identity containing the field of rational numbers. So we can consider the differential algebra always any commutative algebra, defining derivations, trivial derivations on them. Then we consider R over this R differential polynomial algebra in n variables. So this one becomes R algebra, and we take polynomial algebra over R in n variables. We denote this algebra by Cm. So it's one of the main examples here. Where delta it's just usual partial derivatives. Theorem is the following. Let A be a differential R algebra without nilpotent elements satisfying the ascending chain condition for radically closed differential. Then A is equationally Noetherian. So it is direct analog of this Ritter-Radonjic theorem, in fact. Nothing we proved here. But it gives some examples. If R an associated commutative radical Noetherian domain, then this differential algebra is equationally Noetherian. Oh, here I cannot see what. Okay. So now I want to apply this technique to give some results in the case of left symmetric algebras and Lie algebras, in fact. So let theta be set of basic derivations are an arbitrary associated commutative algebra with identity with Q, of course, characteristic 0. Yes. And A be a differential algebra. Differential algebra over this. Consider the space of all elements of this form. So it's Fi is elements here is delta 1 derivation. It looks like somehow we can say it is a set of differential operators, in fact. If you take products of differential operators, then it's not derivation. But if you take delta 1, delta 2, delta m, then you can consider this as a set of differential operators. So in CA, we can proceed, sorry. So we can define on this set product in the following way. Product F delta E, product G delta E. So this in fact delta E acts on G, just. That's it. And with respect to this product, this set becomes left symmetric algebra. Left symmetric algebra, it means it satisfies this identity. This identity. So from this left symmetric, from differential algebra A, we get left symmetric algebra LA. And it's called with algebra of the differential algebra A, in fact. So this one generalizes some construction in the case of Novikov algebras. So in this way, from any differential algebra, you can get left symmetric algebra. Now, left symmetric algebra probably for people here not so interesting, but Lie algebra must be interesting, more interesting, because if you take any left symmetric algebra, take commutator algebra of this algebra, then you get always Lie algebra. So that space B with respect to this commutator, which is left symmetric product and minus left symmetric product, becomes a Lie algebra. And it's called with algebra of this differential algebra A. Sometimes this bracket is called Wronskian, in fact. So we take again left symmetric with algebra LM and the with algebra WM. WM, it is a Lie algebra with algebras. This is left symmetric algebra. So take that differential algebra CM in M variables with standard derivations, partial derivations on the polynomial algebra again. And take it is corresponding left symmetric algebra, then it's called left symmetric with algebra. And Lie algebra of that CM is called with algebra of index, standard with algebra of index M. This is more famous thing, WM, in the case of Lie algebras. So the main result, in fact, so here I tried in order to consider equations over these algebras LM and the WM, you have to have some construction of free algebras in the varieties generated by these algebras. So its construction, it's called usually it is general matrices, in fact, but it is a little bit too. We take many variables here, y, I, j runs in this way, and it takes these derivations yi, which is a linear combination of those derivations. Take the denote by ln the subalgebra of the left symmetric algebra generated by y1, y2, yn, and by wn the subalgebra of the Lie algebra wn generated by this same y1, y2. So the left symmetric algebra ln is the free algebra of the variety of algebras generated by this lm. Okay, so it seems here I denoted by ln, here by lm. It is a little bit confusing. Sorry, I noticed only now. Lie algebra wn, it's free algebra generated by these variables, and the wm, it's a little bit confusing. Sorry. So it is, in fact, it gives description of free algebras. Now, using these descriptions, in fact, so we proved the following theorems. If you take R, arbitrary radical Noetherian domain containing the field of rational numbers, then left symmetric algebra WLM over R is radically Noetherian, and the with algebra WM over R is radically Noetherian. So, in fact, remember I noticed that theorem by Danilova, Remeslnikov. So it is it gives some corollaries in this case. Every free algebra of this variety is equationally Noetherian, and every free algebra of this variety of Lie algebras is also equationally Noetherian. Thank you for your attention. I just want to notice, so it's here, this equationally Noetherian question about equationally Noetherianity of free associative algebras and free Lie algebras are still open. Thank you very much for attention.
Thank you, Professor Ualbai. So, any questions?
Thank you for interesting talk. But is it true that if we consider not only free associative, but free associative and commutative algebra, is it true?
Yeah, it is.
Equationally? Yes.
Of course, the equationally Noetherian by Hilbert's base theorem.
Ah, oh, okay, of course. Thank you. Yes.
Any other questions?
The question is still open for free solvable Lie algebras too. Only in the case of metabelian it's proved.
Ah, metabelian, yes.
Free solvable Lie algebras. This will
Okay. So if there are no questions, let's thank one more time Professor Ualbai. And we'll be meeting after exactly 10 minutes. It's 8:15, and we'll meet at after 10 minutes.
Thank you.
Thank you.
Very much.
Thank you.